So back in 2016, about 8.5 years ago now, I had my great insight into quantum gravity, and I've been exploring this idea ever since, and I've been working upon it, and I've been trying to write books about it and research papers about it and things. And of course, I've done huge numbers of YouTube videos about this idea, and it's generated a lot of interesting feedback, should we say, about this idea. Lots of people seem to like it. I received 654 likes for my page, Sam's Theory of Quantum Gravity, on Facebook. I got 3,000 views and 21 likes on the original video about this topic, and the idea has changed since then. It's or subtleties to do with the idea have changed. The basic idea itself hasn't changed much at all. I still believe that gravitational fields are electron densities, and that surrounding all macroscopic gravitating bodies we find this huge cloud of tunneling electrons which traps light and which exchanges particles with the protons of objects approaching, and therefore exerts a force of attraction over those bodies. So this is still what I think about gravity, and I think it's a very natural, very holistic, very organic way of thinking about the force of gravity. And I think for all sorts of reasons still it's incredibly likely. So I came up with this idea when I was 23 years old. At the time, I'd been studying physics in my spare time pretty obsessively for a few years, at least since university and really since school as well. So I did have something of a background in physics, but after I had the big sort of eureka moment back in 2016, I really started studying physics very obsessively and reading huge numbers of books and research papers and online articles and entries and even YouTube videos, and trying to learn physics to the best of my ability and trying to suss out why we haven't come up with what is really quite a simple idea before now. And I think part of the reason why we haven't discovered the correct theory of quantum gravity up until this point is because the field of the study of gravity has become too mathematized and has become too abstract and frankly too divorced from reality. And a lot of the theories of quantum gravity that have come out in the past, such as string theory and loop quantum gravity, I think these may be curiosities that are very much of interest to people like mathematicians, but not necessarily of great instrumentality in the natural sciences, and don't really explain phenomena that we observe in nature, and need to be updated in line with what experiment and observation tell us about the natural world. So, I mean, building on this idea, like, the easiest way I think to think about this is that it builds a nice parsimony in the way that we think about nature, all the way from the atomic scale to the scales of stars, planets, black holes, and so on and so forth. So in nature, of course, we have atoms. We have atoms with nuclei in their centers, which are positively charged, and then we have a cloud of electrons surrounding the atomic nucleus, which is negatively charged, which is and also crucially reflects light, because the electron interacts very often with particles of light. It also carries a negative charge, which means when it interacts with other particles such as protons, there's a force of attraction there between electrons and protons, and it has the potential to interact with other particles. So this is obviously why atoms are held together. They're held together by the electromagnetic force generated by the positively charged electron and the negatively charged electron and the positively charged proton. So this is why, say, an atom of hydrogen, very simple, one proton in the center and one electron, is held together because there's a force of attraction between the electron and the proton. You might be equally tempted to think about why the atoms are stable and why the electron doesn't simply fall into the nucleus. If it's attracted to the nucleus, surely we must expect it to fall into the nucleus and just, close that gap between it, sort of until it falls into the nucleus. But that doesn't happen, and there's not really a very good explanation for why this doesn't happen. Most explanations that you can find on the internet, I remember Texas A&M University putting out this article about why this doesn't happen, and them saying, basically just saying because quantum mechanics. And I just thought that explanation isn't really good enough. And the explanation that I would give, which is a very important concept in my theory of quantum gravity, is this notion that radiation pressure causes the atoms to be stable, causes the electron to remain in orbit around the atomic nucleus rather than falling into it. And the electron will show up in the nucleus every now and then, but crucially, it's constantly interacting with the background. So it shows up really for a Planck time, a unit of the Planck time, which is about 10 to the minus 43 seconds. Each time almost immediately interacts with a photon and tunnels to a different location. It's then replaced by a different electron tunneling from somewhere else in the universe, which then emits a photon. And this is a consequence of the principle of non-locality and this idea of non-local realism that we get from Alan Aspect and John Clauser and I keep forgetting the other guy's name. Very sorry about that. Who won the Nobel Prize a couple of years ago for that work, which was done in the 1970s, and it's related to quantum entanglement and these sorts of concepts. That the universe is non-locally real. So we find in quantum entanglement, for instance, that the electrons, that it's not the same. Well, it's the two electrons which are bound together in the entangled system, then separated, those tunnel between each other's locations and emit a photon, then crucially reabsorb the same photon, tunnel to the other electron's location, emit it again, and the other electron that was at that location has tunneled to the other location, emits the photon that it had, reabsorbs the same photon, and then tunnels to the other location, which is why in experimental settings quantum entanglement is stable. But just getting back to what I really wanted to talk about, I think that I wanted to build on this idea of a nice parsimony from the atomic scale all the way up to the scales of stars and so on. So we can think of stars really as being kind of like giant atoms, because when we look at stars, what we see really, the everything from the surface of a star down to its center, that's all ionized hydrogen and helium with a little bit of lithium as well, also ionized. There's not really any electrons within the sun. There's electrons will be showing up within the sun from time to time in exactly the same way that the electron shows up in the atomic nucleus from time to time, but mostly for really the overwhelming majority of the times which an electron shows up in space, it's around the sun. It's in the corona of the sun, this kind of atmosphere of the sun, if you like, that surrounds the surface. So this is why we get incredibly high temperatures in the corona, from about 1.8 million degrees Kelvin up to 3 million degrees Kelvin. The corona being this really rather large region around a star where the electrons will be mostly concentrated, tunneling from one location to somewhere else in the universe, being replaced by another electron. The electron emits photon, traps radiation as well. So all that radiation spilling out of the sun, it's getting trapped there in the corona, building up, giving rise to these huge temperatures. And at the surface of the sun, we find that the temperatures are far lower than that. So there's this cold spot at the sun's surface, if you like, where temperatures really only reach about 5,400 degrees Kelvin or so. So this is, I think, probably the most holistic way of thinking about things in terms of gravity, quantum mechanics, and everything else. Because if we think about what an electron needs. If all electrons are tunneling all over the universe all the time, what does an electron need to exist in a given location? Well, it's like what Paul Dirac, it's actually the idea that Paul Dirac abandoned in the 1930s, this idea of the hole conjecture, which is it really needs a hole in the background, an area of completely empty space in which it can tunnel to. And for those of you who know about quantum tunneling does not happen at the speed of light. It happens instantaneously. It happens faster than light, in fact. So we have, at the very fundamental level in nature, we have electrons and other particles really moving about faster than light all the time, really all the time. Giving rise to ultimately the macroscopic classical physics that we enjoy. So yeah, we, I think, need a space in the background in which the electron can show up for any very brief amount of time. These sorts of spaces do occur in the outer layers of things like stars and black holes, but they don't occur there very often. So typically, an electron will show up beyond the sun's surface in its corona. It will show up beyond the event horizon of a black hole, in this kind of huge firewall region around the black hole where you have an immense amount of trapped radiation. Um, the electrons, in the case of black holes, they do tunnel inside the black hole sometimes, as in the same way as with stars, and they pick up some particles there, some photons there, some radiation there, and then tunnel outside the black hole's event horizon again, almost immediately, almost straight away, and then deposit those photons outside the black hole's event horizon. This, over time, causes black holes to lose information, causes black holes to evaporate over time, and this is what we call Hawking radiation. Although I would conjecture that Stephen Hawking was wrong about the specifics of Hawking radiation, that it has nothing to do with the creation and annihilation of particle antiparticle pairs. In fact, in my model of quantum gravity, there is no room for antimatter. And I'm very much guided by Occam's razor in the pursuit of this theory, this model, since I believe that it's a foundational tenet of science that we should not multiply entities beyond necessity. That where the simplest explanation exists and it's tenable, we should take the simplest explanation and not keep introducing things like new particles, new fields, new this, that, and the other, and all these bolt-ons to our theories, which make entities such as the standard model of particle physics really, I think, quite inelegant and quite hulking and cumbersome and somewhat unnatural, somewhat synthetic, somewhat inelegant, I think, is probably the best explanation that we have in physics for these sorts of things. So just rejoining again on this idea of black holes and the possibility of radiating away and things like this, we find they're very, very densely packed with material. So there's almost no space at all in which an electron can show up there. There's this quark gluon plasma, very likely forming the outer layers of black holes. And as for the innermost layers of black holes towards the singularity at the center of a black hole, I'm quite sure I have no idea what they're made of. And actually, my theory of quantum gravity, which is a low energy theory of quantum gravity, has very little to say about black hole singularities. Though I don't deny their existence in nature, and I believe that the detection of a so-called Higgs boson at the Large Hadron Collider, in light of its decay products, I think that smashing these two protons together at near light speed at 128 gigaelectron volts, I think that's very likely to be a naked singularity, and i.e. a very small black hole singularity formed for an incredibly brief amount of time, and then decays into two gamma ray photons, which is what was detected at the LHC. That's the decay signature of the Higgs, conveniently enough. which, yet again, in the style of 20th century physics, just has to be a new particle, because everything has to be a new particle. Because once you discover a new particle, you get a Nobel Prize, and physicists love Nobel Prizes, and yes, they are incentivized by money and the prospect of fame, glory, adulation, love of the public, etc., etc., etc. Because physicists, after all, are only human, and you can say what you like about genius and so on, but I mean, personally, I believe that everyone has the capacity for genius, and everyone has it within them probably to have a very deep understanding of nature. But I believe that what goes along with that very often is a great deal of sophistry and illusion, and that very often we get ourselves into situations where we try to craft the most impressive equations, try to find the most beautiful mathematics, and try to make everything as mathematically harmonious and complex, and such that a handful of people in the world pretend to understand this sort of stuff and may not even really. That's sort of what happened first with quantum mechanics and general relativity, and then much more obviously with string theory, and now we're just into the realms of this stuff that might be all very beautiful mathematically, but is totally divorced from reality and really says nothing about how nature actually operates. And the antimatter problem, I think, can be explained away. I think that quantum gravity is going to force us to remove the antimatter and other particles from our equations in physics. And I think that Paul Dirac was wrong to abandon the Hall conjecture. And I think that, for instance, the positron is not really a new particle discovered by Paul Dirac. I think it's probably a W particle tunneling through a hole in the background, since it wouldn't just be electrons which can tunnel through holes in the background, it can be other particles as well. The W particle tunneling through the background would be very quickly taken up by an electron in exchange for a photon. And this is why we can have positron emission tomography and so on and so forth. And we gained new technology as a result of these phenomena, but I think we've been misreading these phenomena very much. And if we can explain away antimatter, we can also very conveniently solve the baryon asymmetry problem, which is this problem of why matter came to predominate in the universe when, it's been hypothesized this at the beginning of time, all this antimatter was created along with the matter in the universe, that the antimatter and the matter annihilated, leaving behind a tiny percentage of the matter remaining. And I just look at that idea and I don't see it as being physical. I don't see the natural world really operating that way. And I frankly think that there's good enough reasons for suspecting that antimatter doesn't exist, and that it's just different configurations of the standard model particles that we already have at the moment. Because I suppose if you really think about it, with Paul Dirac, he had no idea that there was any such particle as a W particle. He wouldn't have known of such things. That particle wasn't discovered until the 1950s, or even the 1960s. I'm not certain when it was discovered. But it was discovered in particle accelerator experiments, I think in the 1950s, when Paul Dirac was almost dead. Or he died in the 60s. I don't remember exactly. I'm not good with dates and things like that and history of science, but or not off the top of my head anyway, I'm not. But he wouldn't have known about a W particle when he was coming up with his theory of antimatter and positrons and this sort of stuff. And I don't think he should have abandoned the whole conjecture. But And it's not just me who thinks this either, it's other physicists such as Felix Finster, already the mathematician Felix Finster, who's developed his idea of causal fermion systems, which is based on some of the early ideas of Paul Dirac, such as the Dirac sea. And yeah, there are sort of precedents in more contemporary science, more in 21st century physics, that do correspond somewhat with my idea. But I think it's very, very naturalistic and very organic to consider stars to be something like huge atoms, and for these elements of atomic structure to be mirrored all the way up from the atomic scale to the scale of stars, black holes, planets, etc., etc. So yeah, this is I guess kind of the latest update I'm giving on my adventure into quantum gravity. And yeah, reporting from the lovely Surrey countryside where I am at the moment, Swan Barn Farm in Surrey, where I'm volunteering for the National Trust and having a great time here and meeting lots of lovely people and doing some lovely things in conservation and so on. And as ever, it's been a pleasure talking to you. So thank you very much. I'd like to say goodbye now, I think, and I'll talk to you another time. Thank you very much for watching. Bye bye. I love you lots.